All right, one more example to go over to kind of hit home the extraneous solution thing. This problem, just I'm going to tell you right now, it's going to have a real solution and an extraneous solution. And for the real solutions, those can be gotten from the graph. And so what I would do on this, if I'm trying to get an extraneous solution, is I would, or get a real solution, I would just go straight to Desmos if I want a quick way to do it. And I can show you the graphing method here. So with graphing, what you do is you take the left side of your equation and put it into one of the lines in Desmos, like we did with the absolute value stuff. Make sure you get comfortable being able to type stuff in. And I'm a big fan of the keyboard shortcuts, but of course you can use the calculator thing down at the bottom. So you're going to see these weird graphs, and you know they do behave very frantically around certain numbers. That's why they're called irrational. They just act weird. And then the other side of the equation, 5 over x plus 3, is going to be the right side, and then we can see where they intersect to get the real solutions. So the real solution in this case, if I'm looking where they intersect, I see 4. So 4 is going to be what you get if you plug 4 both into both of these equations. You're going to get about 0.714. You don't need the y value, but 4 is one of your answers. So the way that you can get your extraneous solutions from the graph, well, first we got to do a little bit of handwork to get there. So I would take this x squared plus 5x plus 6. It does need to be factored. And if you don't remember how to factor that, that's all right. X squared plus 5x plus 6 has zeros at -3 and -2. So the factors would be x plus 3 and x plus 2. You see how it's the same thing, right? So that's going to be the factored form of it. So let's go ahead and write that down. And what do you notice? Well, we have the same exact factors here. So what I want to do is I want to get all my I want to get my equation written as a line without the fraction bars. So I am going to pull up my LCD, which is x plus 3, x plus 2. And we already have an x plus 3 and x plus 2 there, so we don't have to rewrite them. But what we want to do is we want to look at every fraction and if that's okay with you guys, I'm going to write this as the factored form instead of the original. Now I'm going to put my denominators in parentheses. The LCD, what we're going to do is we're going to just multiply everything by x plus 3, x plus 2. We're going to do it up here. And we're going to do it next to the 5. So what happens is we're going to cancel things out. We're going to cancel out from the first one, x plus 2's. And then from the second one, we got all these except for the 2. So that's nice. And then the third one over here, we're going to cancel out the x plus 3's. So we'll rewrite it as a single horizontal line, and then we don't have any fractions anymore. So we have x in x plus 3. And we have just the 2. And we have the 5 and the x plus 2. Now you can get you can get both the real and extraneous solutions from this point if you'd like to. I'll show you the way to finish it up by hand, but when you get to that point, what you can do is you can say, let me enter this in here again. So you can take the left side of your equation now, you can say x plus 3 plus 2 and 5 x plus 2. Now let's refresh on where the solution was for, well, we're going to take these out first. So remember, our solution originally was I believe it was 4, right? 4 was the one of the answers here. But notice that these graphs not only cross at 4, but they cross at -2. Well, why did that not appear on the original expression? Why was it only 4 on the original equation without the fractions? Well, this goes back to what we were talking about with restrictions, okay? Remember the restrictions said that x cannot be anything that makes the denominator 0. Well, what makes the denominator 0 in the original expression? -2 and -3. Well, because you can't have a denominator of 0, you can't really use -2 as your answer, okay? So that's really an extraneous solution. It's a solution we get when we work out a problem that when we plug it back in, doesn't actually work. I know that's kind of bizarre, but that an extraneous solution cannot be a restriction. So if I'm showing you this by hand, of course, we would want to multiply and simplify this out. So I would distribute this to give you x squared plus 3x. Then you have this 2. And I would distribute that, so that's going to be 5x plus 10. And this is a quadratic, so I would get everything to the left side and solve it out. So subtract the 5x and the 10. And that'll give us x squared minus 2x minus 8 equals 0. And then there's a couple, there's a number of ways to do quadratics. We can do quadratic formula, we can factor, we can graph it like we did before. So you can put that in the graph and click on the zeros. I'm going to factor it, and that's going to give you x minus 4 and x plus 2. -4 times 2 is -8, and -4 plus 2 is -2. That would mean that my answers would be x equals 4 and x equals -2, because we want to switch those signs, because the signs of the factors are different than the actual zeros. They're flipped. But remember, this number here, that's extraneous. So it's not a real solution. It's an extraneous solution, because when we plug it back in here, you get 0, and you can't divide by 0. But you can plug in the 4, that doesn't matter, but the -2 cannot get plugged in, because that'll give you 0 down here in the bottom of these fractions. And so that's going to nullify the whole thing. So this is going to be the real, and this is going to be the extraneous.